Good morning, everyone. We're back. Hi, I'm André Tétreault, Director of Tests and Diagnostics here at VibroSystM. I'm joined this morning by my colleague, Mr. Bernard Lemay.
Good morning, André.
Paul, good morning, Bernard. Paul is away on vacation, lucky him. So I've asked Bernard to give me a hand this morning with this session. So he'll be handling all the logistics and also handling all the questions. So get your questions ready. However, unfortunately, Bernard and I are not fluent in Spanish or Portuguese, but still send your questions. We'll figure it out.
We'll manage.
And if not, well, we'll archive them and make sure we answer them at a future session. So welcome to our 8th Q&A session. Can you believe that? 8th session. Live on YouTube directly from beautiful Montreal, Quebec, Canada, our head offices. I'm very happy to be here this morning to discuss with you, among other things, turbo generators, specifically stator core, stator frame, or end winding vibration. So we've kept the same format today that we used at the last session. The last session we covered monitoring systems for hydro generators. Today we're going to handle the monitoring systems for turbo generators. So we're going to answer the question, what would you recommend for the optimum cost return on investment system for turbo generators? So we have a short video, as we did the last session, we have a short video on monitoring systems, in this case for turbo generators. And after that we have a presentation so that we can go into a little more detail on that specific question. So again, if you have any questions, please submit them and we'll take a look at them.
And also, André, I would like everyone to remember that if you want to submit questions, you have to log into your YouTube account.
Yes.
And we'll keep all the questions that we cannot answer today for future Q&As.
Absolutely. Okay, so without further ado, let's start the short video we have. It's just sort of a rundown on what can be done on monitoring systems for turbo generators. So let's take a look. Okay, so imagine a system that monitors all the critical parameters. Okay, we have a new sensor here that can handle vibration, velocity in fact, and temperature, which we'll get into a little later. And all the information that we have or that we monitor can be sent to your mobile phone. So let's look at the standard system that we've created for you for turbo generators. Okay, so of course, many of the turbo generators, especially the larger ones, are hydrogen cooled. So it's important to have a flange that will allow you to exit all the cabling and all the information in a seal-tight fashion. Make sure there's no hydrogen leaks or limit them as much as possible. So these are factory tested to withstand high pressure, and of course they are very efficient in preventing hydrogen leaks. Okay, so I mentioned we have a new sensor that is available. It's a sensor that allows you to measure the velocity in addition to the temperature. So you can install these sensors as a series of 100 sensors, and you can install them on each individual stator bar. And those sensors will provide you with velocity in multiple directions and also in temperature. So we usually put 36 in the drive-in and 36 on the non-drive-in. Okay. Very small size, real-time 3-axis vibration monitoring and temperature monitoring as well. We also have a shaft voltage monitoring system, which of course involves installing a brush. So that brush is usually installed on the non-drive-in, and using a synchronization probe or using the existing key phaser, it gives us a reference as to where we are. We also have piezoelectric accelerometers for absolute vibration monitoring. We usually install 4 on the frame, 2 on the drive end and 2 on the non-drive end, and 4 on the core, again, drive end and non-drive end. Okay, we usually correlate the information from both. We can see on the left the ones that's installed on the frame, and on the right we have one that's installed on the core. And then we also have fiber optic accelerometers. Of course, if you want to install anything on high voltage, you need something that's completely insulated. So these fiber optic sensors have no metal at all in them, so they're very, very safe for use on high voltage components. We usually install 10 single axis, which we call the FOA 100, and 2 dual axis, which are the FOA 200. So we install 5 on the drive end and 5 on the non-drive end, and we install the FOA 200 on both ends as well to complete the system. So this is a picture of an FOA either 100 or 200 installed. And then we have flux probes to measure the stray flux coming off the rotor. So we have a picture here of a sensor installed on the laminations. And of course, monitoring cabinets, acquisition units, and software to operate the whole system to get all the information available to you. In some cases, it can be sent to VibroSystM. But even if you connect to VibroSystM, all the data is still on the site available for you at any time. And we have result interpretation services to help you analyze the data and get a good handle on the health of the unit. And all this information can easily be viewed on your mobile phone. All right, so that's for our first video. Just turn this off. And why don't we start the presentation? Okay, so turbogenerators. Monitoring of turbogenerators. Well, the first thing that we can look at is stray flux. And in fact, let me just show you a short video on stray flux before we go ahead. Okay, so of course, stray flux monitoring is an issue of detecting possible shorted turns on rotor poles. We use a stray flux probe, as I mentioned in the previous video. And we use a synchronization probe to determine where the poles are, pole A and pole B on 2-pole units. So the sensor is installed on the stator core, same picture as before. And we monitor the amount of leakage flux that comes off the rotor. And we are able to determine whether there are shorted turns by interpreting the amount of leakage flux of each coil. Okay, we have some pictures here of how this analysis is done, and we'll look at that in the presentation because there's no real flux intensity that's correct. It's a question of comparing flux coming from coils on different sides to be able to detect any issues with the shorted turns. Okay, so let's go back to the presentation. So in turbogenerators, the stray flux or the leakage flux of individual slots is monitored in order to determine if you do have turn-to-turn shorts, whether they're present or have occurred recently. Historically, people would usually look at stray flux, not stray flux, but shorted turn issues by detecting behavior of the unit. For example, if you increase the load, and at some point when you do increase the load, the vibration increases. In many instances, that was an indication that you have shorted turns. The second major issue was that if you have to provide megavars and you find out after a few years that you need to excite or provide more rotor current to get the same amount of VARs, that was also an indication of shorted turns, but it didn't tell you where they were, how bad it was, and if you did testing once the unit was stopped, it was not always clear that you could detect where they were. So the issue here is to monitor the flux in the air gap. You have the leakage flux coming off the rotor slot, and you have the armature reaction flux that comes off the stator, and the sensor is able to detect the amount of flux and to be able to compare results and see if there are shorted turns. Problems usually start when the rotor has at least 5% shorted turn. In some cases it can be much more, but usually we don't see any issues until you reach that 5% level. The vibration is caused thermally. It's not magnetically. It's not because you have an uneven distribution of flux. The issue is that if you have shorted turns, you'll have spots on the rotor that will be hot and some spots that will be cold. And that delta in the temperature causes the rotor to bow, to bend somewhat, to change shape. And at 3,000 or 3,600 RPM, I guess that's an issue. So the vibration will increase if the shape of the rotor changes. You will see that when you increase the field current. As I mentioned before, it causes maybe not an inability to produce reactive power, but an inability to achieve previous reactive power with the same amount of current. And in some cases where utilities have a contractual obligation to provide VARs, and if at some point you're no longer able to provide the VARs that you've promised contractually, that can be a serious problem and cause you serious financial penalties. So it's important to make sure that the rotor is in good shape. So monitoring stray flux, the monitoring principle, you put a flux probe, 2 o'clock or 10 o'clock location, and you look at the stray flux pattern that comes off of the rotor. So you can see in the middle you have pole A, and on the sides you have pole B. The flux probe is mounted flat on the stator core or on a wedge. It measures the variations in total flux density, which is the main flux, the armature flux, and the leakage flux. And as this flux is created as each slot passes in front of the probe. So the probe is able to detect the amount of flux at each location. So you get a measurement or a graphic that looks like this. We can see where the, I'll just take the mouse there, Bernard, please. Okay, we can see where the damper bars are, and that's the middle of pole B in this case here, and we can see damper bars on the sides here for pole A. So what we see is the flux of each individual coil, and we can identify using the synchronization probe and configuring the system with the correct number of slots, because not all rotors are the same, and we're able to identify the peaks of each individual slot, and we need to do that to be able to compare the intensity of the flux of each coil from both sides of the rotor, and that's the only way you can actually detect if there's any discrepancies, because if you just look at the raw voltage, there's no real indication what that raw voltage should be. It depends how far you are. There's many different factors. But if you compare one slot on one side and the same slot on the other side, you should get the same flux. So if you compare them, it looks like this. If you take this representation and you flip it over and you compare it to the other side, you get a graphic that looks like this. And only in this case can you actually compare the results of both sides and see if there are any discrepancies between individual slots, telling you that you have a certain amount of shorted turns. In our software, it does that. It compares that, and then it establishes what the percentage of shorted turns is for each individual slot. So this is one of the graphics that our software will produce. And also the software is able to trend. It will trend the percentage of shorted turns for each coil and the zero crossing position. So you're able to monitor long term without taking dynamic measurements, without having to analyze the results in the previous graphs. You can just follow the trends and intervene or go into diagnostics in greater detail if you see an evolution of the problem. Now, another thing that is very important to monitor is stator bar vibration. If you have a turbogenerator that has very, very long end winding that protrudes outside of the stator core. Some of them can go up to 2 meters. Some of them are shorter, but some of them can be very long. Well, if you have excessive end winding basket oscillation, that will put a tremendous amount of stress at the stator bar level. So if this is excessive, this will put a lot of pressure here, usually the first 60 centimeters or the first 2 feet. And if the bar is loose, if the wedging system is not performing well, you'll start creating some tremendous vibration here. And in fact, you'll see almost nothing here because there's a cantilever effect, whereas the vibration will be almost nil here, but you'll have excessive vibration here and to some extent some vibration here. So it's important to monitor what the stator bar vibration is in this location to prevent excessive wear and tear of the insulation as it rubs against the core. Okay, so typically the stator bar vibration increases as the flux or the current increases, and the levels decrease as the core heats up and the bars expand. The end winding vibration also increases as the flux or the current increases. However, in many cases, vibration levels increase as the windings heat up. Now, knowing that the end winding vibration has increased can mislead personnel to believe that the stator bar vibration has also increased. It may or may not be the case. So what I mean by that is some people believe, well, if the end windings are vibrating a lot, the stator bar vibration is high as well. Sometimes it is, sometimes it isn't. It depends exactly how the unit is performing under which operating condition. It's important to remember when you heat up the windings and the stator bars, of course, the copper and the insulation will expand. And I get the question often, how come the end winding vibration is such a problem? I mean, can't they just make it stiffer? And the answer is, well, it looks very easy, but imagine you have to make a consolidated basket that is extremely stiff to prevent vibration, but it also has to be very flexible to allow the expansion and contraction to occur. So you have to make something very stiff and very flexible. That's difficult to do. Okay, so in many cases it's fine, they do it very well, they know how to do it, but it's very easy to make a mistake and have all kinds of issues. Okay, so it's important to be able to monitor those issues to prevent evolving situations where wear and tear occurs, and worst case you have a failure. So one of the tools that we have a series of sensors to do that, but one of them is this sensor here, where in fact the sensor, we can't see it because it's inside. It's glued onto that little bracket we have, that little plate, that little piece of FR4, and the sensor is a capacitive probe that's actually looking at the stator bar. So the semicon paint on the bar will allow us to measure the actual distance between the sensor and the bar, giving us how much vibration is present at that location. Okay, so again, if you have excessive oscillation of the end winding basket, and you have loose stator bars, and of course if you do have high end winding vibration, you can assume that eventually you'll have loose stator bars. You have a high level of stress at the stator bars at some distance inward from the end core. So as I mentioned before, if you look at the end core, where the stator bar exits the core and then starts to rotate and move, depending on the size of the unit, towards the end cap, the vibration at the end of the core is probably where you will see the least amount of vibration. The excessive vibration will be towards the end cap, and of course, again, if your stator bar is loose, if the wedging system is not tight enough, you will have some stator bar vibration, let's say up to 60 centimeters or 2 feet inside the core, and that vibration rubbing against the core will cause insulation wear and eventual failure. Most stator bar failures are in that location. Okay, we have some pictures here of some damage. You can see some cracks, we can see some dusting and evidence of greasing, and all evidence of stator bar vibration. And we have an example here of a raw waveform of stator bar vibration, and we have tolerance levels for how much vibration can occur without having issues. And you can also look at the fast Fourier transform, the spectral graph, of course. We're looking at 100 or 120 hertz vibration mostly, and that's what we're looking for, and that's what we'd like to see to be able to compare to existing tolerances and see if something needs to be done, if it's excessive, or you're in good shape and you can keep operating the unit. Now, for end winding vibration, we have, as I mentioned in the short videos, two basic models. There are models for different insulation classes as well, But we have two basic models. One is for single axis use and the other one is for dual axis use. These can be installed, in fact, on any high voltage component, but they are used quite frequently for end winding vibration. You can see a picture on the right. We don't really see the sensor per se. The installation uses two-level epoxy use. One is used just to fasten the sensor on the end winding, and the second is to apply epoxy resin impregnated tape all around the sensor to make sure it doesn't come off or fly off during operation. So these sensors, the installation process for these sensors ensures that these sensors do not come off. Now, I'd like just to take a brief second here to talk about installation. We realize that installation is a costly operation. We realize also that there are many people on site that have expertise on windings, on end caps, on insulation. However, we strongly recommend that the customers make use of our service department to install these sensors. There's a few ways to do it correctly. There are thousands of ways to do it incorrectly. And as I always say, our customers are very creative. They can come up with new ways to incorrectly install. So it looks easy. You look at a picture and you go, oh, that's easy to do. But there's all kinds of factors, all kinds of do's and don'ts that are not apparent on a picture. For example, routing the cable. There's a very specific way to do that so you don't create a bridge between two different phases. There are ways to install the cable to make sure there's no accumulation of contamination on the cable. I mean, the cable is fiber optic, but if you have tremendous contamination on the cable, well, that contamination can be a path to ground. You don't want to do that. So there are specific do's and don'ts in installing this equipment, and our Zoom implementation experts have all the training, have all the expertise to not only install them, but to plan the installation so that it goes off well. So we strongly recommend, again, that the service department be called upon to do the installation, or at least show you how to do it, so that you don't run into a situation where you install, thousands and thousands of dollars of equipment and nothing works. Okay, so that's just a sidebar. So we have a graphic here that was taken in the States, and we can see some end winding vibration readings in trend format. As you can see, there's quite a few hours involved here. And the interesting thing I wanted to show you is that something totally unexpected occurred when we were doing this test. And if you look at the blue line, and that's the speed of the unit, and you can see that when the unit reached 3,000 RPM, there was tremendous amount of vibration below on the, again, the light blue signal, which is the end winding vibration. And the unit wasn't even excited. They were only bringing the unit up to 3,000 RPM, no excitation yet. So everybody wondered, why do we have such high vibration levels if there's no excitation? And the reason for that is that the unit, which was originally designed for the European market, was modified to be used in the North American market. So instead of a 50 hertz unit, it became a 60 hertz unit. And we suspected that most of the components were tuned to 50 hertz to avoid the 60 hertz frequency. But the thing is that to get to 60 hertz, you have to go through 50 hertz. And we can see that when they reached 50 hertz, the vibration was high. When they decreased lower, the vibration decreased. When they increased back up again, the vibration increased. But then when they moved on to the nominal speed, which was 3,600 RPM, the vibration decreased. So this is a resonance issue. The mechanical 50 hertz vibration that was being transferred to all the components was creating a higher level of vibration simply because they were reaching the resonance of the bar. Other examples here, some of the things that we look for when we're monitoring end winding vibration is the effect of excitation and the effects of active power and reactive power. In some cases, there's no real change or real behavior to observe. but other than usually seeing more vibration when we increase the load, but usually the vibration is still acceptable. But in some cases, if you vary the load, whether it's active load or reactive load, you can see some significant reactions to those variations. And that's part of the testing we do, that we ask the unit to be put through different operating conditions, ramp up speed, critical radial speed, critical tangential speed, and then exciting the unit, and then operating, increasing the load. And we'll ask that the load be varied, and we'll ask that the reactive power also be varied. We want to see different operating conditions which can occur during normal operation of the unit to see how everything reacts and if everything behaves properly. Okay, so we have a case here where we had accelerometers looking at the vibration, and we had reactive power which varied. And varying the reactive power actually caused variations in the vibration. You can see here in yellow, this is the reactive power, and they increased the reactive power. And you can see that the vibration, in fact, increased so much that we reached the actual saturation point of the sensor. And then when they decreased the reactive power, it went down significantly. When they increased again, it increased also. So the active power didn't change, but just changing the reactive power was sufficient in this unit to cause some variations in vibration. Now, the effects of resonances, that's one thing also that we take a look at. In fact, the results that you have on the screen was, well, I can't identify the location, but it was a unit that had a known housing resonance issue. It was not very bad, but it was known. The housing did resonate at 100 hertz. And while I was on site doing some testing, we were taking a look at the trends over time of all the different sensors. And while they were doing that, they made an attempt to eliminate the housing resonance by applying a technique that was developed by EDF, Électricité de France, where they would put a triple ring donut, spring-loaded donut, on the actual housing. And they put 4 of them, 2 on the drive-in and 2 on the non-drive-in, on both sides of the unit, 1 on each side. And once that's installed, they would loosen up the first ring, and that would start absorbing some of the vibration. And they were able to loosen these dampers, and you can see the effects on this sensor here. Whoops, can I get the mouse?
Yep.
I have the mouse, sorry. You can see how when they started to apply that, you can see how the vibration decreased significantly. And then by playing around with it, they could see, they could affect the amount of vibration on the N winding. And that's what was so surprising. They were reducing or modifying the resonant frequency of the housing so that it vibrates less. And that had an impact all the way to the N windings, and also on the ring bus and on the phase drop. So that resonant issue at the housing was actually impacting on all the components of the unit. All the units were suffering from higher levels of vibration simply because the housing had a resonant issue. So that was very, very surprising, very, very exciting to see the effects of that event on the vibration of the entire unit. Okay, so the monitoring of the N-winding vibration is a question of not only looking at the electromagnetic vibration at 120 hertz, but also the 60 hertz vibration. You can see here on a graph that the FFT is showing a reasonable 120 hertz signal, but also a 60 hertz signal. And this was a case we had in the United States, where we found that, again, the 120 hertz was fine, but there was an elevated 60 hertz. And in reality, when we called the customer, we assumed that they were having high shaft vibration issues. And they were surprised to hear this from us, because they were. And they asked us why we could tell that they had shaft issues. And we said, well, we can see it on the N windings. The 60 hertz is transferred from the shaft to the bearing down to the foundation, back to the housing, back to the frame and core, and eventually at the end winding. So this is a case of where very high shaft vibration was actually showing up on the end windings. This other case here is a case where a paper was written about this case where a unit was being built, again also in the United States, and the model that was being assembled is a model that was that existed somewhere else in the world, and that unit had failed within a year, and this customer wanted to avoid having the same issue, so they asked the OEM to come in and do all kinds of testing to see if they were going to have the same problem, and they actually hired a famous American engineering firm to come in and do some serious bump testing. And what they found was that most of the, or all of the bad results were not on the end windings per se, but they were all on the phase leads, which is why the picture you see here on the screen shows sensors installed on the phase leads. And in fact, I think 90% of the sensors installed on this unit, and there were quite many of them, were mostly installed on the phase leads. And that was based on the results of bump tests. And we took some readings, and we found immediately that some of these bars or phase leads were vibrating tremendously. There was a value of 265 microns peak, which of course means 530 microns peak to peak, which everyone agrees is way too high. If you look at tolerances from different associations or different vendors, you'll find variations on what's good, what's acceptable, but everyone agrees that anything above 20 mils or 500 microns is way too high. And remember, this was a new unit. Okay, so evidently there were issues still on this unit that needed to be dealt with. Now, well, to make a long story short, before I move on to stator core and frame, if we look at this example, the OEM and the utility and VibroSystM have been working for quite a few years to monitor this issue. The OEM is very good. They go in there and every year and they try new things to stiffen the end winding, stiffen the phase leads. They've removed all the dry ties, put wet ties, tried different methods. They still have some issues, but I think it's a great example of everyone working together to try to ensure that the unit maintains a good performance, is able to produce power despite the fact that there's a well, noticeable issue on it that if left unchecked would definitely cause a failure. So I like this case because it shows people can all work together and make sure that the problem is dealt with and the unit is kept online, operating, producing power, which of course is very important. Now, in some cases, people also have issues with stator core and or stator frame vibration, and then there's a series of sensors that can be used for that type of monitoring. As you can see on the picture here, we're talking about piezoelectric accelerometers. Some are installed on the core, some are installed on the key bars, some may be installed on the ribs, some are installed on the frame, and the idea in general is to see if amplitudes are high, first and foremost, and then is to look at the frequency content to see if it's pure 100 or 120 hertz, or are there other frequencies present that may indicate a secondary problem. But in our case, the past few years, we've been focusing a lot on not just looking at the amplitude, let's say from the core to the frame, but looking at if they are in phase in an attempt to detect any looseness. Do we see any looseness between the core and the frame? And we have on a few occasions. And looseness between the core and the frame, or looseness between the core and the key bars, creates potential arcing between the laminations and the key bars or the frame. And that, of course, is a tremendous amount of energy and can easily cause a major failure of the core if the laminates start fusing together because of the arcing. Your core might be out of order or might fail completely in a very short period. So we've had a few cases where this was an issue, and one of the things we did was to install piezoelectric. In this case is sufficient because there's no high voltage here. And we monitor closely the core and the frame to see if there's any discrepancy. We do it on hydro generators as well. We do it on sag mills and ball mills. And the idea is to make sure that the structure is sound and everything is working properly. Okay, so we have here a signal from the piezoelectric accelerometer. It should be primarily at 120 hertz. We can see some 60 hertz, again, coming from the rotation of the unit, 60 or 50 hertz, of course, coming from the actual rotation of the unit. If the vibration is excessive, that will be transferred to the foundation and then on to the housing, the frame, and the core. So you usually do see some 50 or 60 hertz, but it's usually very low. And if it's high, well, then you have a problem. Okay, so we see here the spectral analysis of a stator core vibration sensor showing primarily a 120 hertz signature, which is expected. Now, in regards to stator winding, we measure the vibration as I indicated, which is very important, of course, but we also have equipment to monitor the temperature. We have a sensor that can be installed to measure the temperature of the windings coming out of the core. And as I mentioned in the first video, we also have a new sensor that's able to measure the velocity in 3 axes and also the temperature. So that might be an even more interesting product to invest in. So these are multi-point sensor lines. We call them Christmas lights. So you have a maximum of 100 per chain, so it's very easy to install. They're very easy to replace if you do have a sensor for whatever reason gets damaged during an outage. Someone steps on it and breaks it. They can easily be replaced. You don't need to replace the whole chain. You can just replace the sensor. We usually install them on both ends, and usually one sensor for each bar or every few slots. These are not affected by magnetic and electric fields, and they can allow you to produce a thermal map, which will give you an indication of the temperature for each bar. And as I mentioned, the new sensor will also give you the velocity in 3 directions and the temperature to give you a complete picture. So if you have a bar that vibrates a lot and that bar has a higher temperature, well, there you go. The insulation is deteriorating and you might have to go in there and resolve this issue before it gets to a point where the unit might fail. Okay, and also the same technology can be used to monitor the core. In some cases, there's the picture you have here. This is an existing customer of ours that's having excessive problems with stator core temperature, and that compressing plate is also getting very, very, very hot to a point where it's cracking. So we're helping this customer understand exactly why this is occurring. How bad is it when it's in operation? Are there any operating conditions that create more temperature than others to try to avoid those? So we've been helping this customer for a year and a half now, trying to get a handle on what's going on with this unit to try to ensure working operation for as long as possible before they have to go get in there and try to fix this issue. So you can see at the bottom another example of a type of graph that you can produce, giving you the whole stator core view as if it was unrolled, and you can spot areas where it's hotter than others. And that's it for the presentation.
Thank you, Andre. That was really interesting. I mean, from an analyst standpoint,
yeah,
we're used to seeing data and graphs, and it's always interesting to see real-life implementations and how the sensors are laid out.
It's one of the things that is fun from our job. I mean, it's very challenging because we sell so many different products and we look at so many different parameters and different types of units that it's a big challenge to be able to master all of these different behaviors and correlations and all that. But it makes it a lot of fun as well, because when we go in the office in the morning, we don't really know what are we going to look at today.
Absolutely.
Whereas, you know, some vendors have one product, and if you're a specialist, well, you look at the results from that particular product every day, which is fine. But for us, we'll look at air gap, we'll look at end winding vibration, we'll look at core temperature, we'll look at flux, we'll look at turbines, we'll look at shaft vibration. There's so many things that we look at that makes our job, again, very challenging, but very, very exciting. Anyway, for me, maybe I'm just a nerd.
And seeing all those basic parameters that have to be monitored, because if they're unchecked, that can lead to so many issues with the machine itself. For our first question, Andre, I chose a question that was given to us by one of our viewers previously, and I chose something that was in the same, following the same train of thought, so to speak.
Okay.
So our first question here today is, what are the telltale signs of end winding vibration? So.
Okay. Well, we've been asked that question many times before, and I think it's normal because it's a valid question. Again, other than having a monitoring system installed that's giving you high readings and that you know you have an issue, I guess the best way is during outages if it's a hydrogen cooled unit, after you remove the hydrogen and after you remove the end covers, you go in there and you find localized dusting in one area. You know, you go in there and you'll see some dusting, and in some cases you'll see greasing. If there's humidity in the unit, you'll see some greasing, and that's a clear sign that you have vibration. And some people say, well, we thought that was partial discharge. Well, partial discharge will create, in some instances, some powder, but you will see that the powder is caused by discharge between the insulation and a grounded piece of material or another insulated piece of material. You don't see partial discharge between the insulation and a piece of FR4, or you don't see partial discharge between insulation and a wet tie. That doesn't exist. There's no reason for that. So if you have localized dusting or greasing around the support system or next to the core, that usually is caused by fretting, and the fretting will create the dust. And again, if it's humid, it'll create this brown grease that you see leaking. Another telltale sign, which is a little more complex, is when you go in there and there's dusting everywhere, all over the place. So either you have vibration generalized everywhere, or you have some vibration in different locations, but the ventilation is just carrying the dust all over the place. Well, if that's the case, well, you evidently have a problem with vibration. Finally, if you go in the unit during an outage and you see clear evidence of damage, you know, ties that are half broken or completely broken off, support blocks that are dislodged or missing, they're on the floor. Ties is the same thing, they're on the floor. Cracking of the insulation, you know, all of these are telltale signs that you have a vibration issue. So water cooled units, you'll have the water box, or you'll have the cooling conduits that are leaking. That's another clear sign that you have vibration issue. So all of these during the visual inspection, when you stop the unit for an outage, they're all clear signs of vibration. And there are clear steps to be taken to try to resolve these issues.
Someone else wanted to know, also a vibration-related question. He wanted to know, how do you decide how many fiber-optic accelerometers to install, and also where to install them?
Well, that's also a question we get quite often, and it's also a very valid question. And my initial answer as an analyst, so of course I've never actually bought any of this equipment, so budget for me is not a concern. So my answer would be, well, you put sensors everywhere. As many as you can, put them everywhere. But of course that's not practical. Budget is always an issue. I guess what would lead you to decide how many sensors and where would be, again, some of that evidence we just spoke of. If you go in there and you have localized dusting somewhere, well, you might want to focus your end-winding vibration sensors in that location, maybe put a few others in reference somewhere else, but you might focus there. If the evidence of dusting is everywhere, well, what I would recommend then is you do bump tests. In reality, if you suspect that you have vibration issues, end-winding vibration issues, I think that at all major outages, you should plan for bump testing. I mean, it's a known procedure to determine where the natural or the resonant frequency is. And there are standards for that where you have an exclusion zone. You should never have a result in that zone. And if you do that, well, at least you know that you've done everything you can to try to avoid having your windings anywhere near the electromagnetic frequency. So bump tests should be performed at all major outages for sure. Second is, again, if you have evidence of damage, if you have a section of the windings that's seeing ties breaking up, blocks that are disappearing, falling on the floor, these are all indications that should spark or should help you identify how many sensors and where they should be installed. And remember, as I showed you in one of the cases I showed you, the end winding is not always where the vibration is excessive. It's in some cases is at the phase leads. Some cases is at the connecting ring. We've seen quite a few cases where the phase drops were having issues. We had a famous case somewhere in the world where the phase drop cracked twice within 6 months. And they couldn't figure out what was going on. And I went to site to help them try to figure out what the issue was. And what I found is that we noticed that the vibration sensors which were installed on the phase drops were actually suffering from some kind of resonance. You could see the 100 hertz signal, and you could see that there was periodic repeatable cases where the frequency, high frequency would show up on the signal, which for us represents a low frequency impact. Something is actually hitting on the end windings to make that appear. Now, of course, units in operation, nobody is standing next to the winding and hitting it. But it means that the windings which are installed on the stator core and frame, well, that is suffering some type of impact. And we were able to show that if you went from the drive-in, you had some impact there. But as you move closer to the non-drive-in, you had a higher and a higher and a higher level of impact, which told us that the stator was not properly fastened. It was actually moving, and it was giving a jolt at every so many milliseconds. And that jolt, that high energy jolt, was actually showing up on the end winding. Obviously, if you have a major failure, that's also going to give you an indication as to what you should be doing. If you have a major failure on the unit and you want to avoid that, which I assume you don't want to have this occur again, that will help you also identify where you should put the sensors. And in some cases, there's no evidence of any problems. The utility just wants to be proactive and wants to protect the asset, and they decide to invest in some end winding vibration. And in those cases, we have an approach where we simply put them symmetrically all the way around in both ends. I know some people think that the drive-in, since the end windings are much shorter and there's no phase leads, there's a lot less material, that there's no issues there. But we've seen as many failures on the drive-in than on the non-drive-in. So we install sensors on both ends, and then we train the people to be able to analyze the results and get a better idea of the health of their unit.
So basically what you're saying, Andre, is that ultimately it's a question of budget. The more the better. Yep. But there's a way to focus on problems if
correct,
they are found
correct
beforehand.
Yep.
Okay.
Yep.
We have another question related to testing. Let me just show it here. So someone wants to know, couldn't you test for short turns during an outage?
Yes, yes, you can. I mean, historically, that's what people have done. As I mentioned previously, in some cases, people notice that if they increase the load, the vibration, shaft vibration goes up, and in some cases, they realize that they need much more rotor current to produce the same amount of VAR, so they suspect that there's an issue with shorted turns. And what they would do is do testing on the unit while the unit is stopped. There's all kinds of tests. One of the most popular one is a recurrent surge oscillation test or an RSO test. And I think you can actually do them with the unit rotating. Because the problem is that if you have a short turn issue, it might not show up when the unit is stopped and cold. Remember, the unit is operating at 3,000 or 3,600 RPM, so the amount of Gs is astronomical. I think it's like 5,000 Gs, some ridiculous number. And so the components are under tremendous amount of stress, and it is possible that the shorted turn only appears when you're in that condition. And in addition, the coils are hot, they expand. The short might show up there. So there are many reasons why a shorted turn, which exists while the unit is in operation, may not show up stopped and cold. Doesn't mean you shouldn't do the test. It just means that you might do the test and find nothing. So the idea of having a system that is online, at least if you do have these issues, it may tell you, or it may confirm that you have an issue. It might even tell you some indication as to where it is. So if it becomes a problem, or if you're getting close to an outage, you might plan an intervention and go in there and try to fix the issue. So yes, it is possible. There are tests you can do, but a straight flux monitoring online system will definitely help you to get a handle on what's going on.
Thank you. We have another question, a very interesting one. Earlier today, you mentioned that we do monitor the stator core and also the stator frame kind of in conjunction. So the question is related to that. Let me just show it here. Do you know of a case where monitoring the stator core versus the frame has detected serious issues?
Yes, we've had a few cases that we're handling right now. There's a large coal power plant that we monitor. They had issues for some time, and they replaced the stator recently. So we're trying to see if the new stator has the same issue. It doesn't seem to have, but the older one did have an issue where the core seemed to be loose from the frame, and they had arcing issues. We also had a case also in the United States. Unfortunately, it was after the fact. They had issues on their units for them. And we installed end winding vibration and some stator core and stator frame vibration sensors. And we did a whole bunch of testing. And by the time the information was sent back to us, one of the machines failed. And it was a stator frame failure. And when we looked at the data, you could see how the vibration was excessive between the core and the frame. And in fact, the phase was somewhat out of sync. So unfortunately, the machine failed before we even had access to the data. And when we looked at the data, you could clearly see that there was a problem. So yes, we do have some cases. Hopefully, we get a chance to look at the data and prevent the failure. But in this case, again, we got the data and the unit had already failed, but we were able to show why quite clearly. So yes, we do have some cases where we have stator core looseness from the frame. And again, I mentioned we do a lot of that for hydro units as well. And we've been doing it for sag mills and ball mills in the mining industry. They also have structural issues specific to those types of units. So it's important to monitor the air gap on those units and monitor the core and frame behavior, because they do have issues of that type and others as well.
And I guess being proactive as much as possible to avoid finding out after the fact.
Yeah, especially if you have a unit that has an own issue, or you have a unit that has issues elsewhere. You know that this is possible, so it's a good idea to try to prevent it and not just observe the damage and fix the unit afterwards.
Andre, I think we have time for one last question.
Okay.
Someone wants to know, have you observed low-frequency stator core or frame or end-winding vibration, and is it considered a problem?
Well, it depends what it is. Yes, we have. We've seen low-frequency vibration on end windings. When I say low frequency, instead of seeing, let's say, 100 or 120 hertz and the 50 or 60 mechanical, we've seen like 30 hertz, 25 hertz, 10, and that I'm not exactly sure where that's coming from, but usually the amplitude is very low, and most people consider that not a problem. There's no issues. But where you have issues is in the case I mentioned previously, where you could see the frame and the core were actually impacting against the foundation, and that's a serious problem. And that won't show up necessarily as low frequency activity. You will see some, but it's actually showing up as very high frequency, as I said, repeatable, and it's periodic. It's like a beating or a modulation that shows up. That's very easy to see. I have another case, an interesting case that was in the US, where they had older type sensors from a manufacturer, very old, and when they did some major work on their stator, they removed all that and they bought our system and put it in there, and all of a sudden they had high vibration levels that were being picked up. And to make sure they didn't have an issue, they stopped the unit a few times to go in there and take a look, and there was no evidence whatsoever of vibration. There's no dusting, no cracking, no looseness, nothing to report. So they were a little bit flabbergasted. And what they decided to do at some point is to install a sensor on the end core, on the core itself. And lo and behold, they noticed that the core was showing the same thing. So to make a long story short, in reality, the end windings were not vibrating as opposed to the core. The whole thing was banging against the foundation. So the end winding probes don't know that everything is moving in symmetry. I mean, they see an absolute vibration. There's no way for them to tell whether that vibration is as opposed to the core or in unison with the core. And in this case, they were seeing high vibrations because it was lower frequency vibration, and the old sensors did not see them because they were tuned at 120 hertz, so they didn't see anything else. So the 120 hertz was normal, but they had all this stator core movement banging on the foundation that we were able to pick up, and it was showing up, but nobody understood what that vibration was. And that last sensor on the core gave us the information we needed. The end windings were not moving in relation to the core. The whole core was moving. So they went in there and did a better job of fastening the core and the frame, and the problem disappeared.
So you're saying that taking into account the full spectrum helps a lot in these situations? Well,
yeah, as we say in our department, the more information we have, the better position we are to actually understand what's going on. And there's no such thing as too much information.
Absolutely.
Again, we don't buy these systems ourselves, so we like to have as much information as possible, because we know that the more information we have, in some cases it tells you exactly what's going on, and in some cases it tells you that what you thought was a problem, it actually isn't. And then you start eliminating stuff. And like Sherlock Holmes said, if you eliminate all the possibilities, whatever remains, although improbable, has to be the truth.
It has to be true.
Well, we've seen that quite a few times, where we had to say stuff that people say, well, that's not possible. Well, the data is pointing in that direction. And in the end, in most cases, it turns out that we were right. Mm-hmm. So again, that's one of the fun things about our job, is that we get to look at all this stuff. And sometimes we see units that don't behave as you expect them to behave according to the laws of physics. For example, in Brazil, we saw a stator that moved. Well, it says, no, stators don't move. Well, turns out they do. So we have all these interesting things that happen, and we're able to look at all that stuff, and we feel privileged to be able to look at this.
Absolutely.
And help customers better understand what's going on. So, yeah, you assume things work in a certain way, and they're supposed to, but they don't always do, and that's what makes it interesting for us.
Thank you. I think that's all the time we had for today. I would like to say thank you for having me, André.
Thank you for helping me out, Bernard.
It's been quite a while, and
okay.
I'm glad that I was here for the super interesting episode on turbogenerators.
All right. Okay. Well, thank you, Bernard, for assisting me this morning. Thank you all for listening in this morning. I hope you found it interesting. We're going to be taking a break for the holiday season. So don't forget to subscribe to our YouTube channel. Don't forget to ring the little bell if you want to have notifications of new content. All the videos, all the Q&As, conferences, all that stuff remains on our channel, so you can go and review any of these informations. Please continue to follow us on YouTube so that you can be notified of the date and time for the next Q&A session. We'll publish that out very soon. So on behalf of all of us here at VibroSystM and Bernard, myself, we would like to wish you all a super holiday season and a happy new year. So be safe, take care. Thank you all. Bye-bye.
Thank you. Bye.